In this lesson, this lesson is titled Proportions in Triangles. But really what we're going to be looking at is we're going to be looking at proportions that are created by two specific types of lines or line segments. The first thing we're going to look at is proportions that are created when you have parallel lines. And we're going to see that those proportions can be created by parallel lines that cut transversals that intersect to make a triangle, or transversals that don't intersect to make a triangle. So even though this section is titled Proportions in Triangles, we're going to see that you don't necessarily need there to be a triangle for these proportions to exist. What we do need for the proportions to exist are parallel lines. So when we have parallel lines, those will create proportional segments. And also, when we have angle bisectors, that's going to create some proportional segments as well. Now, as we go through this lesson, I'm actually going to be skipping around in the notes. I'm not going to go from top to bottom. And I'm going to change a couple of things around as we go to make things simpler and hopefully a little easier to understand. So the first thing I'm going to do is I'm going to scroll down to the middle of this section of notes. So for right now, we're going to skip the top triangle example. We're going to skip the side splitter theorem, mid-segment theorem. We're going to skip this first example with a triangle. And we're going to come down to the section that says corollary theorem 7.5, the side splitter theorem. And this is going to be a situation where we have parallel lines that intersect two transversals, but those transversals don't create a triangle. So we don't necessarily need to have triangles to get these proportional segments. What we need are parallel lines. So this side splitter theorem says, if three parallel lines intersect two transversals, then the segments intercepted on the transversals are proportional. Okay, so if three parallel lines intersect two transversals, then the segments intercepted on the transversals are proportional. What does that mean? Well, it's a little clearer if we look at the diagram to see what that means. So I'm going to look over at this diagram on the right. Notice I have three parallel lines. How do I know they're parallel lines? Well, I have these markings, the arrowheads, show me that I have parallel lines. And those three parallel lines are intersecting two transversals, this line on the left and this line on the right. And what this theorem says is that these transversals are split into proportional pieces. So on the left, I have the pieces AB and BC. And on the right, I have the pieces DE and EF. And what this theorem says is that however AB is related to BC, DE will be related that same way to EF. So in other words, if AB is half the length of BC, then DE will be half the length of EF. Or if AB is a quarter of the length of BC, then DE will be a quarter of the length of EF. So they're related in the same way. So those pieces of the transversal are broken up proportionally. And you can see here what we did. When things are proportional, we create fractions, cross multiply and solve. So what we did here is we said, well, if I take the length of AB and put it over BC, what's the relationship between AB and BC? Then that's got to be the same relationship or equal to the fraction that I make out of DE and EF. So we're basically just setting up proportions and solving. All right, let's look at an example of this. So let's scroll down to this first example. Well, it's really the second example. This says that the reflection pool in the picture, which we'll get to in a second, is separated by walkways that are parallel to each other and to Jefferson and Lincoln Streets. If the city wanted to add tiles around the pool, how much tiling does X and Y represent? Or in other words, what are the lengths of X and Y in the diagram? All right, so let's take a look at our diagram here, and then we'll work on solving the problem. So this says that the walkways in between the reflection pool are parallel to each other, and they're also parallel to Lincoln and Jefferson Streets. So what I get here, I actually have 4 parallel lines, 1, 2, 3, 4, that intersect 2 transversals, the line on the top and the line on the bottom. And so what that means is, whatever the relationship between 24 and 72 is, I have to have that same relationship between X and 60. Well, in this case, I can see the relationship very clearly. 24 times 3 gives me 72. So that means X times 3 would have to give me 60. Well, you can figure out what that is automatically because just by thinking about it, I can know that 20 times 3 would give me 60. So X has to be a length of 20. But that relationship will not always be that easy to figure out. So anytime we have proportional segments, regardless of whether we can immediately see the relationship or not, we can set up a proportion to solve. And that's what I'm going to do. I'm going to make fractions. I'm going to say X over 60 equals 24 over 72. So let's go ahead and solve for X here. We're going to say X over 60 equals 24 over 72. And once I set up my proportion, I can cross multiply and solve. 72 times X equals 60 times 24. I multiply on the right. 60 times 24 is 1,440. And then I divide both sides by 72. And we do indeed get an X value of 20. 1,440 divided by 72 gives us 20, which we figured out by understanding that the relationship had to be the same there. All right, so we found the value of X. X is 20. Now this example wants us to find the value of Y. So I'm going to go back and I'm going to look at the example here. And again, I can set up proportions. However, 60 relates to 24. 72 has to relate to Y in exactly the same way. Now, this relationship isn't quite as clear. What do I multiply 24 by to get 60? Well, it's not going to be a whole number because 24 times 2 is 48, right? And 24 times 3 is 72. So 60 is in between there. So the scale factor is a decimal. So we can't see that as clearly, but we can still set up a proportion to solve. I can say 60 over 24 equals 72 over Y, and we'll solve just fine. We will get a decimal, but that's okay. That's just because the relationship is not a whole number relationship. So we'll say 60 over 24 equals 72 over Y. So 60 over 24 equals 72 over Y. And then we can cross multiply and solve. Once you set up the proportion, the solving process is always the same. Just cross multiply. And we're going to get 60 times Y equals 24 times 72. Do my multiplication. 24 times 72 is equal to 1,728. Then divide both sides by 60, and we get a y value of 28.8. So y is equal to 28.8. And we said that would be a decimal. And it is because the relationship, the scale factor, is not a whole number. Okay, so we're just setting up proportions and solving. So what happens if we have parallel lines inside of a triangle? So in this first case, we didn't have to have the parallel lines inside of a triangle. They created proportional segments. But the same thing is true if we have parallel lines inside of a triangle. And this is going to be the same process. We're just going to set up proportions and solve. So here's the side splitter theorem as it applies to a triangle. If a line is parallel to one side of a triangle and intersects the other two sides, then it splits those sides proportionally. And basically all this means is that we're going to have pieces of the sides of the triangle that have the same relationship. We can set up proportions and solve. They are proportional pieces. So let's take a look at the diagram on the right to see how we're going to apply this. Here, I know I see my triangle ABC, and I have these two parallel segments in my triangle. The segment in the middle, MN, is parallel to the bottom part of the triangle, AC. And what this tells me is that whatever the relationship between BM and MA is, BN on the right side and NC will have that same relationship. So if BM is 3 times the size of MA, BN will also be 3 times the size as NC. If BM is twice as large as MA, BN will be twice as large as BC. And so what we do here is we just set up fractions and solve, right? The relationship between AM and MB is the same as the relationship between CN and NB. We just set up proportions and solve. All right, so let's look at an example with this. Now, the example that's set up right here is a fairly complicated example. I'm going to simplify this example for you and make it more like an example that you're likely to see on assignments and tests. You're probably not going to see something that's this complicated. So I'm going to go ahead and write down a simplified example. And I'm going to simplify this example by taking segment UV out of my triangle. So I'm going to draw my triangle PQR. Right? So here I'm going to draw this triangle PQR. And I'm going to draw in segment ST, which is parallel to PQR. So I'm going to parallel to PR. So I'm going to draw in ST, and that's parallel to PR. So now I have parallel lines in my triangle, and what that tells me is, however QS relates to SP, QT will relate to TR in exactly the same way. So let's go ahead and fill in our values from the triangle that we have for the example. Okay. So SP is x plus 2, and TR is x. So I'm going to go ahead and fill those in. So I have x plus 2 here, and TR is x. Now, QS and QT, let's look at those lengths. QS is going to be the whole left side right here, so I'm going to include the 12 and the 4. And QT, the right side, is going to be the 9 and the 3. Remember, to simplify this example, I'm just eliminating this segment from the diagram altogether. All right, so on the left-hand side, the length of QS has a length of 16, and the length of QT is 9 plus 3, which is 12. And now that I have this simplified example, it becomes a very simple problem. I'm going to take x plus 2, and I'm going to put it over 16. And that's going to be equal to x over 12. Okay? Or in other words, if 16 is twice the length of x plus 2, then 12 has to be twice the length of x. Or if 16 is 3 times the length of x plus 2, then 12 has to be 3 times the length of x. We have to have the same relationship on both sides of the triangle. So let's go ahead and set up a proportion and solve. I'm going to say 16 over x plus 2 equals 12 over x. As soon as I have my proportion set up, I can cross multiply and solve. So I get 16 times x equals 12 times x plus 2. Remember, the binomial has to go in parentheses so that I remember to distribute. So I'm going to bring this up here. So I get 16x equals 12x plus 24. Subtract 12x from both sides. We get 4x equals 24. Divide both sides by 4, and I get an x value of 6. Now, if I plug that x value in, I'll be able to clearly see the relationship. On the right-hand side, TR, that's x, so that's just 6. And on the left-hand side, PS is x plus 2, or 6 plus 2, which is 8. So now look at the relationships between these numbers. On the left side, 16 is twice the size of 8. And on the right side, we have a matching relationship. 12 is twice the size of 6. So those sides are proportional. Now let's look at a very specific type of segment that we will see inside of triangles, and that is called a mid-segment. And we did see mid-segments back when we were working with quadrilaterals. We did mid-segments of trapezoids. Here we're going to talk about the mid-segment of a triangle. So let's go ahead and look up the triangle mid-segment theorem. Now a mid-segment joins the midpoints of two sides. So this is going to say, if a segment joins the midpoints of two sides of a triangle, then the segment is parallel to the third side, and that's important because the parallel part is what creates the proportions. And then that mid-segment is also going to be half as long as that third side. All right, so let's take a look at this diagram over here where we can see our mid-segment. So in this case, I can see that G has to be a midpoint on the left-hand side. How do I know that? Well, because these congruence markings say I have the same amount of distance on either side of G, which means G is right in the middle, and it's a midpoint. I can say the same thing about H. H also must be a midpoint because I can see that I have congruence markings on either side. So whenever a segment connects two midpoints, we call it a mid-segment. That mid-segment is going to be parallel to that third side. And what's also important here is that the mid-segment GH is 1/2 the length of the third side DF. So if this third side is 10, GH is 5. If this third side is 26, GH is 13. If this third side is 100, GH is 50. You just cut it in half. Because what we have here ultimately is we have two similar right triangles with a scale factor of 1/2, right? Triangle DEF, the larger triangle, is twice the size of triangle GEH, the smaller one. So DE is twice the length of GE. FE is twice the length of HE. And so the third sides have to have the same relationship. DF has to be twice the length of GH. So whenever you have a mid-segment, that mid-segment is half the length of the third side of the triangle. Now let's do a little mid-segment example. Okay, so next to this simplified example that we just did, I'm going to put a mid-segment example. All right, so I'm going to draw in a triangle. And I'm going to draw in the mid-segment. So I'm going to make midpoints. How do I know they're midpoints? Well, I'm going to put congruence markings. And let's call this triangle ABC with mid-segment DE. And I'm going to say AC has a length of 24. And I want to find the value of X, which is the length of DE. Well, because DE is a mid-segment, right? Segment DE is a mid-segment. That means the length of DE is going to be 1/2 the length of that third side AC. So that tells me that my value of X is going to be 1/2 of 24, which is 12. Okay? Fairly straightforward problem. When you have a mid-segment, that mid-segment is always half the length of the third side, or the side that it does not touch. Okay, and then the last proportionality that we're going to deal with does not deal with parallel lines. Okay, parallel lines create proportional segments. But another geometric feature that creates proportional segments is an angle bisector. So here we have the angle bisector theorem, which says if a segment bisects an angle of a triangle, then it splits the opposite side into two segments such that the ratio between the segments is the same as the ratio between the sides adjacent to each segment. All right, that's a lot of words, but let's see how that looks in our diagram. So if we look at our diagram, I have an angle bisector BX. That's my angle bisector. And that angle bisector splits the third side into two pieces, XU and WU, or WX, I'm sorry. The relationship between XU and WX will be the same as the relationship between the other two sides of the triangle, VU and VW. Or in other words, if the left side of the triangle is half the size of the right side, then the left side of my split up side will be half the size as the right side. So however the left side of the triangle relates to the right side, the left side of my split up side will relate the same way to its right side. Okay? So what I did was, or what we do here, is we make a fraction out of the two pieces of that third side. And that's going to be equal to a fraction made out of the two pieces, or the two sides of the triangle, UV and WV. The thing to notice here in the setup is I put UX on top, so that means the side next to it, VU, also has to go on top. And WX is on the bottom, which means the side next to it, VW, also has to be on the bottom. So the key to this problem is just pairing up the numbers correctly in the right parts of the fractions. All right, let's look at an example of how to use this angle bisector theorem. What is the value of GH and GK? Now notice here it's not asking me for the value of X. So I'm going to have to find a value of X first and then plug that back in to get my actual values. All right, so what I'm going to do is I'm going to make a fraction out of the two pieces of that third side. HK is an angle bisector, and I'm going to make a fraction out of the 3x minus 7 and the 12. So I'm going to say 3x minus 7 over 12. And now I'm going to create another fraction using the side lengths of the triangle itself, the 3x plus 3 and the 18. But the key here is wherever I put the 3x minus 7 in my first fraction, the 3x plus 3 has to go in the same place. So since I put 3x minus 7 in the numerator of my first fraction, 3x plus 3 has to go in the numerator of my second fraction. And wherever I put the 12, I have to put the 18 in the same part. They both go in the denominators. Once you get the setup for the fraction correct, then you just cross multiply and solve. Then this problem becomes no different than any of the other problems we've worked in this section. So I'm going to cross multiply. And again, we have binomials, which means that I have to put my binomials in parentheses. So I'm going to get 18 times 3x minus 7 equals 12 times 3x plus 3. And then we're going to distribute the 18 and the 12 into the parentheses. 18 times 3x is 54x. 18 times 7 is 126. And then when we distribute our 12s, we get 36x plus 36. All right, so I'm going to rewrite this equation up here so that we can solve it. 54x minus 126 equals 36x plus 36. I'm going to get all my x's to one side by subtracting 36x from both sides. And I get 18x minus 126. That cancels out, and I'm left with 36 on the right-hand side. Now I'm going to add 126 to both sides. Just our normal algebraic solving process. It's going to cancel, and I get 18x equals 162. Divide both sides by 18, and we get an x value of 9. So that's great. We got our x value. But remember, the question is asking us for the values of GH and GK. So what I have to do is I have to take this 9, I have to plug it back into 3x plus 3 for GH and 3x minus 7 for GK. So let's go ahead and do that to finish off this problem. So GH is 3x plus 3. And I plug in my 9 for x. I get 3 times 9 plus 3. 3 times 9 is 27. 27 plus 3 is 30. Same thing for GK. I'm going to plug in my 9 for x. GK is 3x minus 7. Plug in 9 for x. 3 times 9 is 27. 27 minus 7 is 20. And so we get our values of GH and GK. GH is 30 and GK is 20. Okay. And that's how we solve these problems. Set up proportions and solve. So we get proportions created by parallel lines that cut transversals into proportional pieces. And we also get proportions created by angle bisectors that cuts a third side into proportional pieces.